All right, so we're looking at our first example problem. We're looking at two functions that represent cost of costs for fuel, projected costs for fuel. One, kind of the standard projection for 2012 through 2024. A second one, a revised projection based on if the engines change to be more efficient engines. So this function, in fact, is kind of the top function. This is the bottom function. So my area calculations, the space in between those two, we are going to set up as top minus bottom. Now, for these application questions, we're not usually going to get intersections. We're going to get some kind of interval decided for us. So the fact that this particular problem says, let's talk about this over the range of time from 2012 to 2024, kind of artificially sets up some boundaries for us where, so 2012 and then 2024 would be kind of like right there. Let me move that out of the way. 2024, so not this part. Just looking at and since 12 to 24, because that is the nature of the model. The T in the model is being represented by a 2-digit number, where 2012 represented with 12, and so on. Once we understand that this is how to calculate this type of thing, it isn't any different from what we did in our class last time. It is just an area between two curves. The fact that we've got the technology aspect to do the calculation for us makes it just all the easier. So a little bit of Math 9. If we're doing this on the handheld, 12 to 24 and 2.21. Now I'm going to just use X because on the graphing calculator, that's just an easier variable to get to. It's the default variable on this key. So you can do anything in terms of X. Doesn't really matter what the variable is it's written in. So you'll see that happens a lot with me when I use the graphing calculator. Any variable it's written in, I just kind of say, oh, that's going to be X this time. And when you get to the end of the integral, don't forget, you've got to put that differential term, that D, whatever. If these are in terms of X, then you have to have dx. And that looks familiar. We got an answer of 47.52. And let's see, I'm going to write this. I'm going to do a little shortcut here. I figured out, actually, they're not in terms of X, they're in terms of T. We figured out that C1 was the top function and C2 was the bottom. Do not assume that that's the scenario. I could have very easily written this problem where I talked about the new model first. And so I could have called this guy C1 and this guy C2. Problem still would have had to have this one first because that's the one that has the greater cost. I'm looking for the difference between the cost from this function and the cost from this function. So what do we get? 47.52. And so if we wanted to explain what that meant, I could say something like new engines are going to save $47.52 million. And you got to be careful about this. It's total. It's the total savings over the 12-year period. That would be important if you were a person that was sort of trying to help make an argument that the company needed to purchase these engines, and you said, we're going to save $47 million or $47.5 million, you better be pretty clear that's over 12 years, because it'd take you 12 years to make that savings, because if you have to go 50 million up front for the engines, you're looking at more than 12 years to recoup. And probably at that point, you've also got labor costs for repairs. So that may not be worth it. Just saving money, you got to consider other pieces. If I say, oh, look, it's going to take us, it's going to cost $8 million to upgrade our engines. We'll save $47.5 million over 12 years. So we're saving around $4 million per year. That means in about 3 years, we'll have less than 3 years, we'll have recouped the money we've spent. That maybe sounds a little bit more reasonable to a board of directors or something like that. Okay. Especially if maybe this isn't a private company. Maybe this is a government thing. Maybe this is a township, a county thing, and they're saying, okay, well, we're going to do this. We're going to raise taxes to help offset the cost, but we only have to raise them this much because this change will offset the cost as well by saving us money. People may or may not be willing to vote for that. It just kind of, So this would be one piece of information in potentially a proposal to make a change. And the people doing this calculation may or may not know that they're doing calculus. Okay, they wouldn't necessarily have these at their disposal, but they would have financial system software that would do this kind of calculation for them. But somebody had to program that, and that's where the calculus came in. All right, questions? Okay. So, 2 to try. I'm going to give you like 15 minutes and then we'll do them together. This is same kind of concept, very similar nature to these problems. In this case, it's consumption of petroleum. There's a particular model for consumption of petroleum. This is the projected model, and then something changes and we realize this is actually going to be the consumption model. See what the difference is between the two models, how much petroleum is saved if we can operate at this consumption model, maybe because we've made some kind of changes, some kind of improvements, so on. And then number 3, similar question, revenue modeling, 2 different revenue models. Which model projects the greater revenue? How much more revenue are you going to get from one model versus the other over this period from 2015 to 2020? All right, so give those a shot, and then we'll check them together.
When it's a lot of long equations like those, can we shorthand it to just C1, C2 as label?
When you write it down, yes, absolutely. That's what, yeah, and that's kind of one of the reasons it's nice to have them labeled. It also, I don't know if you guys remember, but we talked about this last time. We'll leave. If we go into Desmos, let me do this, okay? And do the same thing, label our equations. Now, we can't use the same letter like C1 and C2, but if we want to use like C and D, we could. So let's say I said C of X equals that big scary function, right? When I go down here and I set up my integral, I can use C of X instead of having to retype all those pieces. So yeah, it's definitely nice to use some function names to make them a little less annoying to write. I always tell my AP students to do that because, you're taking a time test. You want to do anything you can to save time. And so not having to write out the whole function, just writing out the name of it. It's kind of why they usually give the functions names. Oops, that has to have an X in it or it's not. Okay. Oops. Poop. Just that, just that. X. Squared. There we go. And then, pretty sure, I don't know, yesterday when I did this problem, I got 2 different answers. So I definitely want to make sure I do this one right now. Because one of those had to be wrong. Okay. Now we do have to graph these to see which one's above and below. Graphing on Desmos, a little bit of zoom out with the negative sign will help you. Hopefully even though this has the really kind of weird coefficients, it's essentially just an x cubed function, just with a lot of nastiness. It's a cubic model. So you've got something that looks like a basic cubic function. Okay, kind of that same little wiggle for boring old x cubed. I'm going to call the second guy this one. 0, 0, 0. So 0.0067 x squared. If you want to do them in terms of t, that's fine. This just would have to be t's out here as well as t's there. 0.211 x. And once you're zoomed in on one, you should get the other one. Oops. Helps if we type it right. Okay. So the cubic model was sort of the initial model for the petroleum consumption, and based on maybe new regulations and things being more efficient, whatever, we're looking at an adjusted model. So this is what we thought was going to be the plan. This is more what looks like the plan. Okay. If I want to get that a little closer in, I can. So there's the 2015 mark and the 2000, we're doing 35 or 25? Yeah, 35, okay. So we got to look in the stem of the problem in terms of what we're actually calculating. So we're looking at the difference in the two models between 2015, or x equals 15, and 2035, x equals 35. So I'm going to absolutely take advantage of what I've got sitting here. Throw my integral in 15, 35. C of x is the top one minus d of x. If you try to do this without the integral or the integration differential, without the d part at the end, it'll just yell at you. If you don't put grouping symbols and you throw the dx and you have it like that, then they're going to be like, I don't know what you're talking about. This is fine. I should have thought about using that d, but it's looking for an end set of parentheses and then a closing dx. So yeah, and that's what I got fourth period yesterday. So I don't know what I did second period to get a different answer. I have to look back at my work, but this looks more like what I got. 142.616 repeating. So yeah, so 15 to 35. In terms of these models, C1 minus C2, they are in terms of D. And what did we say? Oh, 142.616. 142.616 repeating, and that is 142 quadrillion BTUs of petroleum, okay? And that's over the 20-year span. So from 2015. So it's this much, this many BTUs over 20 years. If we wanted to find per year, okay, we would take that 142.616 divided by 35 minus 15, or 20. Okay, and get like 7.1. Hi. Thanks. Okay. Rima, this is, yeah. Okay. 0.2616 divided by 20. There you go. Yeah. So we're looking at about 7.13 quadrillion BTUs per year. Okay. If we wanted a per year amount, if we want an individual year amount or an average per year, we would take the total change in the y's, total change in your functions, compared to the change in your x's, the change in your time. Rate of change of output compared to the change in your input. Slope. Lots and lots of things in the world just come down to a slope. So total change, total difference, average difference. Pretty straightforward. Definitely easy. Makes it much easier to do this. When I give you names of the functions, you may not be able to use them in Desmos, but you can absolutely use them to do that. I don't know. I mean, it might. Does it let you do? I didn't try. Let's see something for a second. If I do C sub 1 of x, I'm just trying it. Some stuff, that's how I do it in Desmos. I'm like, let me just see what happens if I do that. Okay. It seems to be okay with that. So I bet we're about to break ground. It doesn't mind it. Yep, okay. You can use the same letters. You can give them the subscript. You just have to make sure, it won't work with that. Oh wait, or maybe it will. It does? Oh, but that's different. It doesn't give the same answer though. So I don't know that it understands, like it's doing something here, but it's not doing the same. Oh, I do have those. If I take those out, will it work? Just curious. Oh, yep. All right, there you go. Yes, you can do it that way. Most of the stuff I figure out on Desmos, I just try like, well, I wonder if this will work. This is how I figured out you could look, I just tried that, it worked. Awesome. I love that. It's even better. Okay, so C1, C2. So, but here's the thing. Watch this. I bet if, yeah, it won't understand that. So you got to pay attention. However you write these guys, they have to be in terms of the same variable, and that has to match it. That x. So if these were t's, it doesn't matter out here, but if these are like in t, this would have to be dt. Otherwise, it doesn't know what you're doing, and it does something else with it. Because it is possible to have an integral with two different variables. That's multivariable calculus. Okay. All right, sweet. Let's do the last one. Revenues. Revenue models. These two revenue models are kind of close to each other. I'm still recording, aren't I? Yeah, okay. Let's pop these off. Let's get rid of all this. Oops, not like that. Okay. Oh, and I'm going to use my new trick. Okay. Which is not going to work for some reason. Maybe because this is popped up. Yeah. If my keyboard's popped up, it doesn't understand. So R1 is 7.21 plus 0.58 T. I go back to my normal like house zoom. That's not a bad picture. You know, zoomed in or zoomed out, you can definitely get more data. Little house kind of takes you back to the normal, kind of like the Zoom 6 on graphing calculator. Equals 7.21 plus 0.45 T. Okay. Click and hold, you can change colors if you feel so inclined. And you can change what the lines look like. So if you're like, I want this one to be dots. And you can really tell the difference. Okay. So the first one is the dotted line. The second one is the solid line. The dotted line is the top line. And so when we integrate, we're going to, and if you don't erase everything, you can just kind of retype over. Let's see. This particular problem asks us to go from 2015 to 2020, so that's what I'm going to do, except I'm going to do 20, not 10. And I'm going to do R sub 1 minus R sub 2. Now, check this out. No grouping isn't going to like it. If you group in the front, it's automatically going to stick the back one at the very end. So you got to kind of squish up here and squeeze the back one in there. There we go. So 11.375 looks like our calculation for example 3. That 15 to 20. R1 minus R2 dt 11.375 billion more in revenue from the R1 model. Okay. So bigger revenues for this, 11.375 billion more, and that's over the 5-year period. Okay. Once again, that kind of information is important because you're like, well, it's more, but it's this much more over this interval of time. What else is going to happen over that interval of time? You know, if we have to, whatever other, you know, aspects we have to consider, that may or may not be positive. Given all the pieces of a company working together. That's it. That's as easy as it gets. They're all kind of the same. You're doing the difference between the two, whatever the context. It's exactly what we calculated last class. Top minus bottom, left and right, even easier sometimes because the left and right function of the functions, the borders from the left and the right are given.